Okay. Okay, so hello everyone. I'm Igor, and today I would like to show you a strategy of how to reduce dynamic compilation latency by using concurrent and parallel dynamic compilation. So let's jump right in. What is it that we want to improve here? So in any kind of virtual machine or dynamic compilation system, code is initially interpreted, or you run sort of an unoptimized version of it. And this is to have fast startup, because that's what interpreters are good at, is startup speed. And then as we go along, frequently executed code is compiled on the fly. And once it's compiled, we can switch from interpretive to native code execution as soon as dynamically compiled code is available. And as we all know, this interpretive bit at the beginning is slow, and sort of the natively highly optimized code that we generate at runtime, that's fast, somewhere around a factor of 10 difference. So what my talk is all about today is I want to show you what we did in order to enable an earlier transition from this interpretive to native execution mode. So what we were trying to do is make this interpretive bit at the beginning, where we discover application hotspots and compile them, much smaller, so this transition can be done earlier, and you can remain in this highly optimized code for longer. So let's look at an example. And it really, when you're trying to reduce dynamic compilation latency like that, it's really an end-to-end thing, right? You can't just say, I'm going to build a faster code generator, because that's not the whole thing that contributes to your latency. So there are many places that kind of need to work together to be able to effectively reduce compilation latency here. And it also depends on how you design your VM or dynamic binary translator. There are virtual machines where dynamic compilation is on a critical path. Let's say you start executing your target application, you profile it, you discover that there is, let's say, some methods or a hot loop, you consider it compilation worthy, and then you would stop execution, start dynamic compilation, and then once it finishes, you will then link whatever you compiled and start executing in native mode. Now, when you have dynamic compilation like that on the critical path, then of course, if you want something that has fast startup times and needs to be interactive, then you can sort of have delays because you have to wait for compilation to finish. And you also have to make trade-offs. If you want startup time to be fast, then your dynamic compiler probably won't do as many optimizations in its first run, because you want code to be available quickly. So state-of-the-art systems what they're trying to do is get the dynamic compiler out of this loop, and run it in a concurrent thread. Now what that means is that when you start executing your target application, you have this bit at the beginning where you start interpreting, then you discover something that you would like to profile. Let's say you discover, oh, here's a loop. So you start to look at it, or you see that you're executing a function or method frequently. And once you discover that there are hotspots, you kind of note this fact and then dispatch the compilation to a concurrent JIT compiler thread. And once that guy is finished, it registers the native translation, and then your sort of execution loop can perform this switch from interpretive to native execution. And you see this bit, which we like to call the critical path. So that's what we like to make smaller. So, and as I said, it's an end-to-end thing. So there are kind of two things that we need to look at that are critical. The one, of course, is the discovery of frequently executed code. So here at the beginning, we need to be really efficient and fast. And we also need to come up with a strategy of how we can, so once we have discovered application hotspots, how we can somehow improve the throughput of our dynamic compiler. And so you will see that we're adopting a sort of concurrent and parallel. So we've designed a concurrent and parallel JIT compilation system where we think that, so I'm going to show you some results. We think that we're doing a pretty good job at that. So just to reiterate, there are sort of what's the solution to the dynamic compilation latency problem? What are the things that we need to look at? We need to improve the code discovery or profiling. So this is how do we figure out what's frequently executed efficiently? And of course, we need to improve the throughput of our dynamic compilation subsystem. Now you heard me talk about code discovery and profiling, and you may wonder by now, so well, how hard can that be, right? So just output there some code that does profiling, and well, you know what's going on. Well, it kind of depends on which program representation you're working with. So there are program representations where, for example, instructions can be easily separated from data, and that's virtually true of any kind of structured programming languages such as Java, JavaScript, Common Intermediate Language, or Java bytecodes. So for these kind of program representations, you can even statically ahead of time precompile your target program. So there's really no difficulty to discover what, let's say, a control flow graph. You can just look at a function or a method or even a loop and just discover what's going on in there. But we're in the instruction set simulation business, or dynamic binary translation, and there we're dealing with a slightly different program representation, which I kind of classify here as those are binary programs in the form of hardware machine instructions. And there it's not possible in general to look at it and compile it statically up front. So for any kind of frequently used instruction set, these are all way too complicated to do that because the control flow heavily depends on on what happens dynamically at runtime. Now this isn't anything new. Already in 1980, it was Horspool and Moravec that kind of proved that if you just the problem of identifying executable, so separating instructions from data in a binary is kind of is equivalent to the halting problem and therefore sort of unsolvable in general. So if there's just no way to look at a binary and precompile it up front. So that means that all the information that we get about, so when you're doing dynamic binary translation or instruction set simulation for such instruction sets, so you have to incrementally discover code in hotspots. So this is just kind of I would argue that's an additional difficulty because if you're dealing with a language VM, then you have static and dynamic information available. Unfortunately, in our context, there isn't much static information available for us. We have to discover most of the things dynamically, which means that if we want to be performant, then that needs to be designed well. So how does our code discovery work? So as I said, it's incremental. So if you look at this kind of timeline over here, where we have this trace interval, which is we like to call them trace intervals. I get to a moment to it why we call them that way. And here you see there's a sequence of interpreted basic blocks. And effectively, the way we discover code and profile it, we sort of look at, we store basic block entry points and control flow edges. And at the end of such a trace interval, what we're left with is effectively a dynamic control flow graph. Or we also, in research, you need to give these things fancy names, so we call them regions. So this is how we kind of do code discovery, right? So now once we've discovered regions and then kind of pick out frequently executed code, how would we go about then? So this is kind of first bit, and the second, so the first bit in terms of how do we discover hotspots, and the second bit is how do we actually compile them quickly into highly optimized code. Now for that, we'd like to look, so here's a sort of a running example where I can show you the benefits of using this concurrent and parallel JIT design in order to reduce this critical path. So let's assume we're running a single-threaded application. We're simulating it in our instruction set simulator. And one of the differences in our system to others, to other dynamic binary translators, is that we sort of start profiling or kind of this trace recording the dynamic execution trace right away, right from the start. Because for us, even the first basic block could already be something that's frequently executed. Typically, other systems, what they do is they just kind of wait until they find a specific structure, like a loopback, and if that's executed frequently, then they start to record control flow. So we do that right from the start. And then we do a different thing, or another thing that's really different to any other system out there, and it is when we decide to actually dynamically compile something, well, what you would usually do is you look at execution frequencies. So, if you have a method or a frequently executed loop, and if it's, if you're on loop iteration 50, and your frequency counter for that loop kind of overflows, then you would decide, okay, this is something I would like to compile. We're doing it slightly differently in the sense that we don't use an overflow of an execution threshold to trigger dynamic compilation. We just kind of let, we record what's going on for a certain time. Now this is where the trace interval come into play. And then at the end of such an interval, we kind of look back quickly and see, well, what have we recorded so far? Was there anything worthwhile for compilation? Now, the reason why we do that is to kind of have reasonably sized compilation units that we can then effectively compile. Okay, so we break this tracing intervals, and then you see how that kind of fits in well with a concurrent and parallel JIT, because over here, if you look from this interval 1, so after this interval 1, we've discovered a hotspot. You can dispatch it for dynamic compilation. Your first just-in-time compiler thread can start working at it. And now here you see the advantage of a concurrent system, and that is we don't wait until that compilation is finished. Execution continues, and we may even find a second hotspot and a second trace interval. Now, if we only had one concurrent JIT compiler, that we would have to wait until it's finished before we can start working on the next one. But because it's parallel, we have several of those guys. The second JIT compilation worker can start dynamically compiling the second hotspot. So you see that this is kind of where we're able to hide compilation latency. And another important thing is because when we were designing the system, one of the things that we wanted to have is, so we kind of thought about, okay, what are all the features that we want? And one of them was, well, it should be very interactive. It should be fast. We should be able to switch to this native code as fast as possible. Should be able to exploit today's multi-core architectures for this, and all of that led to to one very important thing, and that is the execution loop. We should really try to never stop it at all. So all of this, that's why we chose this kind of concurrent design of the dynamic compiler. Now here, what's important as well, that once the compilation are finished, that we need to somewhere store the results of them. We somehow need to let the execution loop know that, hey, for this piece of code, a compilation, so we've already compiled something. Now that happens also asynchronously, because if you think about it, when you design the system, right, your interpreter or that execution loop would somehow need to check, well, is a compilation already available or is it not? And let's say you would lock. You would need to synchronize on that. That would, of course, slow you down. So we've built sort of so registration of compiled regions is asynchronous, so the execution loop sort of will, in time, discover, oh, something's been compiled, and then can transition. Now, so can transition into native mode. Now, if we kind of play this a little further, we'll see that, for example, in this application, in interval 4, we've actually discovered several application hotspots. And this is sort of another feature of this design, is that you can really exploit the task parallelism that you have here. Because these are all independent compilation units, and you can start working at it. And now you might think, well, haven't static compilers been doing this? They've been doing this for a long time, right? So you can, with your build system, you can somehow say make J8, and they do sort of this parallel compilation. But so far, no one has really looked into bringing this into a into a dynamic compilation system, because of the problem that how do you efficiently? You have to somehow extract this parallelism, right? It's not there for free, especially from a single-threaded application. I mean, how do you parallelize that compilation? And also in our context, remember, we don't really know until runtime what our code looks like. So this is all something that we discover dynamically. And so all the choices that we make here are runtime choices. So this is one of the things why probably no one else has really looked at this up until now, because it's difficult. Now, this was kind of the high-level example, and to show you kind of the benefits of a concurrent and parallel JIT. Now let's look at how you kind of go about designing it. So this is the execution loop. So you'll find something like that in I would argue in any kind of VM where you sort of start executing your target program, and if you start out interpreting, and then you kind of check, okay, for example, do I have something that's already in native code for this basic block? If that's the case, well, that's great, because then you can transition to your native code and start executing there. If not, well, then you have to do sort of profiling or this code discovery. And for us, we'll do that until the end of a trace interval. And at the end of a trace interval, we kind of analyze what's been going on and extract sort of frequently executed regions. And we dispatch them to this translation priority queue and then immediately continue execution. And this translation priority queue, this is we use this abstraction. It's a concurrent and shared data structure, and it acts as the main interface between the execution loop and our JIT compilation task farm. Because the execution loop is sort of the producer of workload for the dynamic compiler, and the JIT compilation task farm kind of picks these things out of the translation priority queue. And then here, this is where LLVM comes to play, or we're kind of users of LLVM here, where we use the LLVM framework to build this concurrent and parallel JIT compilation task farm. Because here in each JIT compilation thread, what we do is we have our own internal representation of what we recorded. We apply some of our own optimizations there, then generate LLVM AR, run some of LLVM's optimizations over it, and then sort of use the JIT to compile and link code. Now, if you think about this, you see that we're using this translation priority queue here, and maybe some of you have wondered, it's a priority queue, so what are we prioritizing on, right? So if you think about it from an end user's perspective, right? So if I'm using a VM, and what I care about is that the code that I'm currently executing and that's frequently executed, that's really important to me. So that should be the stuff that the dynamic compiler should really look at. So what we've done is we just built in a dynamic work scheduling strategy that kind of looks at recency and frequency and uses that to sort of reshuffle in this priority queue to prioritize kind of what you're running frequently right now for the dynamic compilation worker. Why is that important? Because remember, the system runs concurrently. And that is, so your execution, so while you may have dispatched something for the dynamic compiler, your execution may have continued, and you may have entered a different hotspot. So you don't want to waste time compiling stuff that you're not running now. So this is why you need some sort of prioritizing here. So if new things come along, you need to prioritize them if they're frequently executed. Now, how do we arrive at? So what do we need in order to prioritize things like that? Or compilation units or the hotspots like that, we need a notion of frequency and recency. And both of them are sort of available for free in this design, because we have frequency because we need to record execution frequencies, and we have a notion of time because of these trace intervals. Okay, so we know, and these two things is effectively what we use to kind of sort things correctly in this priority queue. And then there was another thing that was annoying us in other sort of VMs or dynamic binary translators, and that is that hotspot thresholds are sometimes hard-coded. Okay, so the guys that design the system, they usually, they run their set of benchmarks, and then they empirically determine, okay, it makes sense, if we start dynamically compiling a method or a function or whatever after it's reached a certain threshold. Where we kind of thought, well, why doesn't the system adapt automatically, right? Why? Because this obviously depends on the application and on the machine you're running on. And we really don't want users to specify this. And so for this, like with this design, this is actually fairly simple, which is good. Simple is always good. Because what we're doing is when we started executing, we're using a very aggressive hotspot threshold. And if we discover that, oops, this was too aggressive, then we kind of back off and adapt it. Well, how do we discover that something that we've been too aggressive about considering things for dynamic compilation? Well, simply if this queue grows beyond a certain size, well, then we've generated too much workload. That means we can adapt we have to bump up our hotspot threshold. And conversely, if the queue, if we're able to compile all the compilation units in there and kind of get smaller, then we can start to be more aggressive again. So this kind of dynamically adapts the hotspot threshold to your application workload here. So how would you go about? So this was kind of the architecture, if you like, of the system. So what would you? What I want to do here? I mean, I can't show too much code, but I want to show you the main components and concepts. So that you can exploit yourself, sort of, or build a parallel JIT with LLVM. Because if what LLVM offers, or the reason why we went with it when we started to design the system is, as we all know, it's modular and it provides these nice abstractions for us, so we don't have to worry about all the underlying details, or most of them. And the key components from LLVM that actually make the work with the LLVM JIT so nice is that there is a really cool abstraction called the LLVM context for all of the the core global data that a compiler, or in this case LLVM, deals with. So it kind of owns and manages all of that. So we don't have to go in there by hand and put in synchronization, because the problem in a JIT, if you start sort of parallelizing it or running it concurrently, is that typically these compilation frameworks, they have lots of, or they shouldn't have, but they sometimes have global data that needs synchronization. You have data structures that are globally accessed. So, and these are all the things that we don't want to, we as users don't really want to worry about. And this is what these kind of abstractions give us. So this is kind of to the LLVM context, wraps up everything that a sort of a JIT compiler instance needs. And then there is, Eli has yesterday also mentioned it, the LLVM execution engine, which is another great abstraction to just sort of quickly instantiate an engine that can JIT code. And I'll give you a short sort of code snippet how easy it is to instantiate and use it. And of course, LLVM comes with a set of state-of-the-art optimization passes that you can just kind of take and mix and match, or in theory, you can mix and match them in any way you like. So this has been, so these are kind of the key components that we use. Just to quickly reiterate, the key concepts for this design are, of course, so that you have this this execution loop, kind of dispatches compilation units via this priority queue, and then you have this JIT compilation task farm where each JIT compilation thread has its own instance of an execution engine. Sort of, it's really a little compiler on it, a little JIT compiler on its own, and it kind of pulls the compilation units and compiles them. And of course, the asynchronous registration of compiled native code. Okay, so if you were so let's say you would like to, after this conference, you'd like to go home and quickly check out how to build a multi-threaded JIT. So let's say you would implement your JIT thread class, and you would have some sort of a thread-based class. Then these are kind of the main components that you need. Per each JIT compilation thread, you need your LLVM context, and sort of each engine needs some type of main module. It's also then thread private for each thread. And then, of course, you need your execution engine. So now when you would instantiate that thread, you would, of course, you need to instantiate these data structures. Fortunately, that's also very easy. You just sort of call their constructors. And even better for the engine, there is another great abstraction called the engine builder. And that's just sort of a one-liner, or well, here, for formatting reasons, I've made it into 3 lines, to say, well, please give me an execution engine, or give me an instance of an execution engine. Now here you have the choice, because there are several implementations of this interface. You could either use sort of an interpreter execution engine, or you could use sort of the classical JIT, or here you could even say, well, I would like to have MC JIT. So, and then once you've instantiated it, so how would sort of your run loop look like in your JIT thread. So what you typically have here is, it's run loops of threads. It's kind of it's a forever loop here where we kind of check this priority queue with translation units. If there's no work for us to do, well, then we just kind of go to sleep. But if there are compilation units for this JIT thread instance, well, then we just kind of quickly grab them, and we'll apply some of our own optimizations. We generate LLVM IR, and then we call this sort of one method, which is called getPointerToFunction, passing it sort of LLVM IR code. And so when all the magic happens inside that method, where sort of the LLVM IR that we generated will be just-in-time compiled, then sort of linked and loaded, and what we get back is a pointer that we can sort of jump to and start native code execution. And of course, for us, we'd also have to somehow register that that we have a translation available for this particular code that's being executed. Okay, so this is kind of the necessary framework for this. You see, it's not too complicated, right? So you can really, after a conference, you can have a look at it, and maybe you could use it in your own projects in some way. So I've been talking to you. I've been showing you kind of what are the benefits, what's the overall idea, where does the improvements, where do they come from? Showed you a little bit about the design. Now, does it work? So we've done an evaluation. This is we presented this last year at PLDI, and so when we developed the system, for us it was working great. But in order to prove it, we really had to run lots and lots of benchmarks. So we took over 60 industry standard benchmarks from BioPerf, SPEC CPU, Embassy, and CoreMark across many different domains to kind of show that even for the extreme cases, we still get performance improvements from this design. So we've taken all of these. Now remember, we're in the sort of dynamic binary translation instruction set simulation business, so we built them for our target platform, which is an ARC compact ISA. It's a RISC ISA, and we're sort of targeting the ARC 700 processor. And so we ran it on a pretty much nowadays standard quad-core machine, because sort of what we wanted to achieve is that if you run your simulations, your instruction-accurate simulations, we don't want sort of customers to buy expensive hardware, right? You should be able to run this on your standard desktop machine, still get good performance. So I'm going to start with the results for BioPerf. So BioPerf is the benchmarks where we expected our system to do really well, because it's sort of the poster child for it, because there are lots of hotspots, changing hotspots. BioPerf is a computationally intensive, condensed computationally intensive medium to long-running life science applications. And yeah, as I said, it's well suited to demonstrate how this kind of the efficacy of our system. So I'm always going to show you three bars. The first one is the speed up, or in fact the slowdown. So it's just an interpreted only version, so no dynamic compilation that's going on. And then our baseline is a version where we only use one concurrent JIT compilation thread, so kind of state of the art. And then we contrast that to using a concurrent and parallel JIT. And here you may wonder, well, so how many JIT compilation threads are you using? So for all of the results that I show you, we're using 3. And why we're using 3, I'll come to that in one of the next slides. So what is sort of a good number here? So in here for BioPerf, you can see that, I mean, for some benchmarks, you really get phenomenal speedups. Like for ClusLW, where there are many, when you start out aggressively and you have several JIT compilation workers, you can, there's lots of work to do, and if you're able to do it and compile things quickly into efficient native code, then you can transition from interpretation into native code execution so much sooner, which gives you these kinds of speedups. Now, of course, for very long-running benchmarks, that don't have that many hotspots, there's just not that much work to do for a dynamic compiler. So, of course, the speedup relative to your whole runtime there isn't that much to gain. So you may not see that much. So here, for example, for CE, we only achieve a speedup of 1.01, but if you consider that this benchmark runs for a couple of minutes, okay, so that's not bad either. And if you care about startup time, then it's certainly a good strategy to use this concurrent and parallel JIT compiler. On average, there's a sort of a speed up of 1.3x across this benchmark suite. And I also put down sort of the hard numbers, so the simulation rates. Just please note that we've done this. So these numbers have slightly improved. This is from the publication that we have. And so 217 MIPS on average. So what do we mean by that? So remember, we're running a RISC instruction set on an x86 instruction set. And we're able to simulate 270 million instructions per second from this target instruction set from our compact on x86. So let's now quickly look at sort of one end of the. So we wanted to also show that for benchmarks where you would not really expect that much of an improvement because they're very long running. Remember, if you have very long running benchmarks with only a few application hotspots, then there isn't that much that our technique could gain you because, as I said earlier, in relation to the overall runtime, the time you spend on dynamic compilation isn't too big. So in here, SPEC CPU is actually a good, so these are all CPU-intensive benchmarks where JIT compilation time only contributes, well, this kind of marginal fraction to the overall execution time. And again, but even, so here we'll see that for some benchmarks like GCC, where, well, here the GCC compiler is executed, and of course what we then have to simulate or translate is a compiler that, performs, that goes through all these, through the compilation pipeline, and there, of course, you could potentially discover many application hotspots. And what you would like to, so if you actually have, if you can compile them fast enough, then you can get really good performance speedups here. And you see, but even for long-running benchmarks, we're still doing pretty good. So there's the important thing is that you can't lose out with this design. So we're always at least as fast or faster than sort of our baseline. And again, the sort of the hard numbers in terms of simulation rate that we're able to achieve. And then finally is the sort of at the other end of the scale are the very short-running embedded benchmarks from Embassy and Cormark, where some of these, even in interpretive mode, run sometimes below 2 seconds. Right? So for such a benchmark, a JIT compiler can do much there. And so here, what we want to show with this evaluation, that even for that extreme case, where you might argue that even the startup of the system, that we actually spawn 3 JIT compilation threads, so that would maybe slow it down, that still that we're able to achieve overall, there's never a slowdown, and overall we have a 1.13 speed up on average across the whole benchmark suite, which then translates into sort of 392 MIPS in terms of simulation rate. Now, maybe you remember I said earlier, we chose a configuration where we would use 3 parallel JIT compilation threads. Well, how do we come up with the number 3, right? So what is the right number of JIT compilation threads? So how far does it scale? Well, the answer to that, it kind of depends on the application you're running. So there are these applications that potentially could produce a lot of workload for a dynamic compiler because they just have many hotspots. It also kind of depends on your hotspot threshold. So when you decide to actually compile something, and this is for here, for example, it's the case for BLAST-P from BioPerf, for GCC from SPEC CPU. Because what you see here is on the x-axis the number of JIT compilation threads, and then on the y-axis sort of the speed up that you're able to achieve by sort of adding on more and more. So for BLAST-P and GCC, those are sort of good examples of where it makes sense to keep on adding more and more, and the curve kind of tails off for GCC somewhere around 8 or 9 JIT compilation threads, so it doesn't make sense to add any more. But then there are sort of other benchmarks like bzip2, there's just one sort of hot loop, and so adding more than 3 JIT compilation threads, and when you start up sort of your VM, that doesn't make sense. It's after 3, there's no more work that you could actually exploit here. And for all of the benchmarks that we had, so we ran this on a proper multi-core machine, so where there are enough resources available so that we can get meaningful results. And we've condensed this into this cumulative histogram here to the top right, where what this histogram shows is sort of the percentage of benchmarks that show a benefit from a certain amount of JIT compilation threads. So you'll see for all of the benchmarks that we were running, it showed that, for example, 3 JIT compilation threads is sort of the sweet spot where all of your benchmarks show an improvement. Okay, so, and you'll see that if you add, 7 or 8, and still 50% of your benchmarks show an improvement by having that many JIT compilation workers available. So now, of course, the main thing, or the main metric that we've been looking at is end-to-end runtime, because that's effectively what matters to the end user. But there are also other key performance metrics that are important, and one of them is the throughput of our dynamic compiler. So for this, we took the GCC benchmark and said, well, okay, let's try to be really aggressive, sort of with the hotspot threshold, so almost consider anything that's executed a couple of times for dynamic compilation, and let's only run it with 1 JIT compilation thread. So, and then you see, so this curve kind of demonstrates the throughput per time. So how many compilations is the subsystem able to sort of to spit out into optimized native code? But of course, if you have more than 1 JIT compiler, this looks really different. So you're able to get much more work done. So you're able to achieve a higher throughput. And of course, if you remember also the average queue length of this trace translation priority queue, of this translation priority queue, you know, if you would run this benchmark again with a very aggressive hotspot threshold, you know, it could grow to pretty insane lengths. But if you're able to sort of to work it off by having several dynamic compilation workers available, you're able to reduce that as well. Okay, this is just kind of another views onto the same thing. So what this design kind of buys you. And now I'm almost at the end where, you know, you may wonder, well, so far, you know, he has only shown us a single-threaded application. So does this design work for multi-core or multi-threaded environments? Well, and the simple answer to this is yes, it does, because you know there's nothing. So if you look at the design itself, it's what it means to execute or to do dynamic binary translation for multi-threaded, multi-core applications is that you effectively have several producers of workload for the dynamic compiler. And the rest of the system really can scale up with it because, you know, you just have several guys that are putting things into the translation priority queue. And, you know, so this, the short story here is it works well. We had a paper about this recently. So it scales efficiently. There are a couple of optimizations that make it run even better. But in principle, so it scales. That's the main message I want to get across. So finally, so what, the conclusion. So I hope when you walk away today, you will find that that LLVM really is a sort of a good framework for doing JIT compilation, and it allows you to do things that that no one else has done before because of this modularity and it's being easy to use and the abstractions that it provides. So we were able to, you know, with this kind of incremental or interval-based region code discovery scheme that kind of enables this concurrent and parallel JIT compilation, even for single-threaded applications, we're able to deliver really good reduction of execution time, so, you know, to speed up the performance of our programs, and sort of this. And we've done this, you know, through all of sort of the key components that I've been showing you, sort of the being able to use reasonably large compilation units that kind of expose optimizations or opportunities for optimizations, enough opportunities for optimization for the dynamic compiler. It's kind of dynamic work scheduling and adaptive hotspot threshold selection. And of course, the concurrent and parallel JIT. Now, finally, if you're like me, staring at bar charts, usually at conferences, it's really boring. It's a bit hard to imagine what the performance of the system is. So I brought a couple of demos, and these are all going to be live. So please bear with me. I hope they don't crash. I'm kind of using a development version here. But what I want to show you is there are two things. One of them is we've taken video decoding and playback as one of our benchmarks. So we've just sort of downloaded the vanilla WebM sample decoder from, I think Google owns this now, WebM, from their website, and compiled it for our target platform and sort of executed. I'm going to execute it in our instruction set simulator, and it's going to be sort of instruction accurate simulation. So at any point in time, you could kind of stop it and inspect your target architecture, because we're also the back end of debuggers, for example, and then you would always find a faithful representation of the architectural state there. And finally, I want to show you sort of what a full system instruction accurate OS simulation looks like, where there are many more complicated things that we need to care about, like interrupts, exceptions, context switching from the operating system. So now I'm going to execute it in our instruction set simulator with our concurrent and parallel JIT enabled. So you'll see that this has an extremely fast startup time. Please remember, this is instruction accurate simulation. So at any point in time, you could stop and inspect the architecture we're simulating, and it will be sort of the state that we model is faithful to that architecture. So now here to the right, I turn debugging on so that you can see that the JIT is actually doing something, and the various JIT threads are doing something. So this TW stands for translation worker. So here you see that translation worker 5 sort of JITted a translation unit and registered the machine code. And here, for example, translation unit 1 or 0 or 3. So you'll see that we'll kind of keep all of them pretty busy. By the way, this is the latest video from Danny McCaskill called Industrial Revolutions. Okay, so let's kind of see what performance, what simulation rate we'll achieve from this. So, so here you'll see we achieve something like 642 MIPS. So that's pretty good. So let's maybe start it up again to kind of show you this fast startup time. Okay, so you'll see this is almost instant, and it plays in real time. So this isn't, you know, if you're doing development of video codecs before your target hardware is available, I mean, this is a pretty neat experience because it's not slower. It's actually, well, depending on your simulation host, sometimes even faster than Final Silicon. Okay, so while this example is quite nice to look at, it's still hard to imagine what a concurrent and parallel JIT, what that technology really buys you. So in order to demonstrate that, what I'm going to do is I'm going to run two simulations side by side, both of them kind of doing video decoding and playback of the same video. And so then we have the sort of head-to-head comparison. Okay, so what you'll see here is that the simulation with 5 JIT threads has, of course, it has a faster startup. That, of course, means that the peak performance is reached sooner. Well, this is, of course, due to the fact that we have more more dynamic compilation worker threads that can handle the dynamic compilation workload. So, I mean, you can now see that the video with 5 JIT threads is clearly ahead of the one that's using just 1 JIT thread. I mean, eventually, the simulation using only 1 JIT thread, you know, reaches its peak performance. But as you can tell down here, we've already finished playing this trailer. While up here, we're not there yet. Okay, so this one is finished as well, so let's look at the comparison. So in terms of performance, what we'll see is that the one where we had 5 JIT threads had a simulation rate of 413 MIPS, whereas the one where we had only 1 JIT thread had a simulation of 362 MIPS. So you see that there is a considerable difference here, or a significant difference.
So now finally I want to show you a full system instruction-accurate simulation of a full operating system where web and video decoding and playback runs as a user-land application. So first of all, what this kind of benchmark, what it mainly should show you is that our technology also works in the context of self-modifying code, the simulation of interrupts, exceptions, and timers, of course, as well as real hardware devices. So, for example, the screen device is is a model of a hardware screen device, just as the UART, for example. So what you see here is that we started up a Linux kernel here built for your compact platform. And so the first thing that's kind of automated here as soon as the console is hit is that we're starting web and video decoding and playback as a as a user-land process. And well, you can see that you can sort of even interact with the system, and yeah, this works reasonably well. So it is interactive. Hotspots warm up very quickly. You can see that the simulation rate here is pretty good, considering that this is instruction accurate full system simulation of an OS.
Okay, and with that, I think I'm finished, and the only thing that's left is the thank you slide.